the 26th of January, and we are in our second day of studying Chapter 2. Today we are going to talk about heat and work, and we're going to develop an equation that will talk about the conservation of energy for closed systems and start to develop a way of addressing the math of energy conservation and energy conversion. So let's go over to the document cam and we'll kind of pick up where we left off. So we've talked about the ideas, first of all, that energy is conserved, and we've talked about the units of energy, and we've talked about intensive and extensive energy, and we've also talked a little bit about rates of energy transfer. And the next thing is that when we do an analysis, when we do an energy analysis, we break it up for the most part into either an open system or a closed system. And if you have an open system, that means that energy and mass may cross into or out of the system, may enter or exit the system. But in a closed system, no mass crosses the boundary. No mass enters or exits. Right. There's a third kind of a system that's not very interesting from a thermodynamic point of view, but a system that is called an isolated system. It's a type of a closed system, but it is one where neither energy nor mass enters or exits. So an example of this would be the perfect thermos. So if you put hot coffee into a thermos and the thermos were perfect, you'd come back 15 years from now and it would still be at exactly the same temperature and exactly the same energy state, and you would have exactly the same amount as you did when you started. So that never happens, and also from an engineering point of view, it is not very interesting because there's really no mass, there's no equations that we can run, no changes that occur. So what we're going to talk today is about a closed system where we have no mass that enters and exits. So there's a lot of examples of this. One of the types of examples that we talk about frequently in thermodynamics is a piston fitted with a cylinder, or piston fitted into a cylinder. And the reason that we're interested in this, you can add energy to the system or take energy away from the system, and the piston rises and falls, and therefore the volume of the cylinder or the fluid within the cylinder can change, and yet no mass enters or exits. So the only thing that enters and exits are forms of energy, and specifically in a closed system, energy only enters or exits in the form of heat or work. So in other words, what I'm telling you is that heat and work can enter or exit a system without having any mass enter or exit a system. Every other form of energy requires mass. So let's just think about what this means. If you have a piston and cylinder arrangement and you heat it up, the volume increases, right? But the mass of the substance in the cylinder remains the same. If you put a stirrer in it and you stir it up, you put some work into the system, and yet you don't have any mass entering or exiting. This is very different from an open system. An example of an open system might be a sink full of water. Okay, you're going to go out and wash your car, so you want to fill a bucket up with water. You put water into a bucket, you put your hand into it, and it's too cold. So what would you do at that point, do you suppose? Might turn on the hot water? Right, you turn on the hot water and you put more water in. So the energy to increase the water's temperature is brought in by the flow of mass. Another way to do that would be if you put it on the stove. Putting a 5-gallon plastic bucket on the stove is not a good idea. So would recommend against it, actually. So that's the kind of a difference. So we're talking about energy that can be associated with mass and energy that's associated without mass. And the upshot is the only type of energy that crosses into a system boundary that is not associated with mass is either heat or work. So we're going to talk about what those two things are. Heat, which is abbreviated or uses the letter Q as a symbol, is energy that moves from one location to the other, in this case either in or out of the system, due to a temperature differential. So this is the first little piece of common knowledge that we have to expel from our minds in terms of scientific thinking. This means specifically heat is not the same as temperature. And often I did it this morning. I came in and I said, it's really cold, or I go to my wood-burning stove or my multi-fuel stove and I say, the stove is really hot. Well, I'm not really talking about a quantity of heat. I'm talking about a temperature, right? And they're not the same thing. Temperature is a potential, there we go, and heat is something that moves based on that potential type of energy. So two analogies to this. They're not exactly the same, but they may help you to visualize this or to think about this. If you have a waterfall, water goes over the waterfall. Water moves based on a height differential. And I bet I have to readjust this. Hang on. Okay? In other words, the water always moves from a higher location to a lower location, right? In the absence of a siphon or in the absence of some backsplash. But the natural flow of water is downhill. The difference in height between the top of the waterfall and the bottom of the waterfall is not the water, but it's what makes the water move. That's the same analogy between temperature and heat. Temperature is not heat. Height difference is not water. Water moves because of the height differential. Heat moves because of the temperature differential. So, if you have a house, you're living in your house, and you turn up your thermostat to 82 degrees because you like it to be nice and toasty, and you go away for the weekend, so you turn your thermostat down, and you think, well, I left it at 82 degrees, and it's going to stay at 82 degrees. Is that really going to happen? Not really. It's going to be chilly when you come back if it's chilly outside, because the heat moved from the inside of the house to the outside of the house based on the fact that the house is at a hotter temperature than outside. What happens if it's really hot outside in the summertime? It's the exact opposite. And it's like, there's an old joke about a thermos, and the guy says, I put hot coffee in my thermos and it stays hot. I put cold water in my thermos and it stays cold. How did the thermos know? Well, the thermos knows because of what's going on outside, right? The heat moves always in that direction. If it doesn't move in that direction, in a refrigerator, for example, or involving air conditioning, you have to drive the heat in the opposite direction. And by drive, I mean plug something in or combust some propane or expend some energy to get the heat to move in the opposite direction. But the natural flow of heat is from hotter, meaning higher temperature, to colder, meaning lower temperature. Okay, water flows downhill like this unless I drive it back upward. Now, there's another example too, if you're familiar with electricity. If you have a battery and you have positive and negative terminals, that is voltage difference. We just call it voltage, but it's really a voltage difference. And that is not energy. Voltage drives, well, if we do it this way, it drives the flow of electrons or the opposite of the flow of electrons. We're still undecided about which way it goes, but this is basically the pattern, is if you have a higher voltage or a higher potential, you will drive a flow of electrons to another side. And the voltage potential is what causes the drive. So if you disconnect your battery in your car, what happens? It don't go, right? It's pretty simple. It just stops. So that's the way that voltage works. It drives electricity. So these are just two analogies to talk about the difference between heat and work, or heat and temperature. And I really emphasize this because it's so easy, and in everyday language, you don't have to quit talking how you talk. You don't have to correct people in your lives and say, oh, heat and temperature are not the same thing. However, in this class, they mean two very, very different things. And if you get them mixed up, your equations are going to come out to be a mess, and you're going to do everything wrong. So that's why I say it like 10,000 times. All right. So the other interesting thing about heat is there are basically three different manners or ways in which heat moves. And they are all related to each other, and they all induce the other type of movement. But basically, we have heat conduction, heat convection, and we have heat radiation. All right. So for conduction and convection, I would use an example of a baked potato sitting on your counter. So let's say you turn on your oven and you make yourself a baked potato for dinner. And it's sitting on your counter. That's kind of that's a good Idaho potato. That's not like the kind I grow in my garden that are all bumpy and high and weird, but that's easier for me to draw. So potato's hot, room is cold. What happens to the potato as it's sitting on your counter? It cools down. That's right. So mathematically, what we would say is the potato has Q going out into the room. Okay? Now, convection is if we have the same potato, only we want to use it to heat up our room, which is a really strange idea, or we want it to cool off faster, and we put a fan here, turn on the fan, air blows over the potato, and it cools off the potato faster. Okay? It carries away the heat. Air is not a really efficient convection method. Actually, putting airspace in things is a good insulator. However, moving air will move heat a little bit quicker. If you really wanted to cool the potato down, still it would taste disgusting, but you could put it in cold water, and that would be a much better way because water has a very high specific heat. Okay, but now the interesting part about it is that if you look at conduction, the air here is hotter. In other words, the temperature here is higher, and the temperature here is lower. So what do you think happens right here? Hot air is lighter than dense air. And so what you get also, even if you don't put a fan on it, is you get an air current set up around your potato, which is called a convection current. So if you have the potato and you leave it on the counter without the fan, it's going to cool down probably slower, but you're still going to get some convection that is induced, and the word for that is induced convection. That also happens more dramatically with wood stoves or pot-bellied stoves or any sort of a heating appliance. If you have certain kinds of wood stoves do not have blowers on them, they'll still heat up the whole room. It just takes it longer to get out into the room. Doesn't produce less energy, just that you'll have a hotter spot right at the location of the heating source, and it will take it longer to spread out and get into the rest of the room. So it's a little bit more, in one way, it's not an energy conversion way, but you can think of it as being more efficient to have a blower in most cases. Same idea. Okay, what about radiation? All right, well, here on Earth, almost all of our energy, and all of our energy indirectly comes from the sun, right? There's a huge, vast expanse of deep space in between the sun and the Earth, and yet the sun creates radiation energy, and everything here on Earth warms up. Okay? Deep space did not heat up between here and here. In both conduction and convection, the medium in between these two things has to heat up, right? When you have colder and hotter, in other words, everything heats up in sort of a pattern, and it's a sort of a, I wouldn't say exponential pattern, but it's a decreasing spherical pattern, or a decreasing pattern that's similar to the shape of the body that is extruding the heat. In radiation, the space or the medium in between the source and the sink, or the source and the receiver, is not affected. And that the receiver is actually affected by the characteristics of the receiver. So, for example, black stuff, like blacktop, gets hotter, absorbs more heat, and bounces it back. Lighter colored stuff absorbs less heat and bounces less heat back. So if you're a kid and you're running around barefoot in the summertime, do you want to walk on the blacktop or do you want to walk on the sidewalk? Probably on the sidewalk. That is exactly correct, because you can really burn the bottom of your feet if you walk on something dark. And colors are chosen for things based on how much they absorb heat. So that's kind of interesting as well. Now, these are just sort of the basic three methods of heat. There are a conversion thing that I'm thinking of. It's not either of these things, but it's something to talk about, where we can convert heat into different forms of energy, is using solar panels. And it takes, what a solar panel really does, you have something that is, you face it toward the sun. So in our hemisphere, they're generally south-facing. And basically, you have a substance, a semiconductor, which just means that electrons have a slight preferential pathway one way or the other, but that the electrons can move either way. But when you heat up the solar panel, the electrons will start to flow in one particular pattern, and that's called a piezoelectric effect. And the piezoelectric effect will cause a flow of electrons. So it's a little bit different, but it's an interesting process as well. It takes some really specific qualities of materials within a solar panel to make this happen effectively, but it is a conversion process. Okay, so now the other way that in a closed system energy can move in or out of a system is through work. Now, you probably remember that work, the differential of work, is equal to a force acting through a distance. Okay? So what that means is if there's no force, there's no work, and if there's no distance, there's no work. So something has to move in order for work to happen. So if I push on this table, I can push on this table all day long, and I can use all my strength to do so, and if the table doesn't move, how much work did I do? 0. That's exactly correct. So work has, what I'm getting at is that work has a specific definition in the same way that heat has a specific definition. And it is specific to what we do. Now, if I sat here and pushed on this table all day, if I did push-ups on it and just worked as hard as I could, I would feel work. My body would do work. I would probably expend calories, but there's no physical work being done on the table if it doesn't move. Okay? So once again, that's just a different way that we might use the term work from the scientific definition. But for work to occur, we always have to have a force, and we always have to have some distance traveled. So going back to this idea of there's a lot of different ways that work can enter or exit a system, but if you look at this piston cylinder, that I was telling you is very common setup that we talk about, mostly for the expansion of gases and for phase changes of liquids and gases in containers. But if we have a situation where we add energy, probably in the form of heat, to this piston cylinder, and if we raise the piston so that we have some original volume and we have some expanded volume, we have done work because the piston has moved. We've put a force on it from the pressure of the gas or whatever's in here, and we've moved it through some distance. So for this situation, a cylinder piston arrangement, we can take a look at this differential. dW is equal to F dot dr, or the work done from 1 to 2 is equal to the integral of F dot dr. Now, another point that we'll talk about more, but work is an inexact differential, so the integral of del W is not like delta W. There's no delta. It's not like work at 2 minus work at 1. Work depends on how you get from 1 to 2, so it's always an inexact integration. So writing this would be incorrect, or writing this would be incorrect. So it's just the work done from 1 to 2 is equal to the integral of F dot dr. Well, if the force is from a gas expanding, we can think about force over area equal to normal stress, or pressure. Let's just call it pressure. Okay? And then we can say that force is equal to pressure times area. And that area would be the area of the piston, wouldn't it? So we have some pressure from the gas exerted on the area of the piston, and that creates that amount of force. So if we take a look at our integral then, we can say the integral of PA dot dr. And if we think about the fact from here to here, the area of the piston remains the same. Area of the piston remains the same. So AdR, the area of the piston times the difference that we moved, this would be the dr, is really going to be the change in volume, or dV. So for this particular kind of an arrangement, we can say, therefore, the work done by raising a piston is equal to the integral of P dot dV. And so that makes for some interesting consequences, doesn't it? If we have P as a function of V, we can then integrate that directly. Or if we have a curve of pressure versus volume, we can find the area under the curve. Okay? And those are the things we'll talk about in a little bit, not necessarily today. All right, so putting these ideas together. Oh, there's a couple of interesting things here, just for a second. They talk about, they have a section in here called the historical background of heat. And people didn't understand heat for a really long time. I mean, we were very effective at building fires and moving things without really knowing what was going on. So one of the interesting ones that I like, there was a theory that the ancient Greeks upheld, and it was held for many, many years, many centuries, that if you have, for example, a log, and you set it on fire, and it burns up into a pile of ash and, of course, heat, right? That effect was known. Well, the ancient Greeks noticed that if you weighed this log, that it would weigh more than the ashes that were left after you burned it. And so they deduced that you were losing a substance from the log that actually became heat. This is not true, but that's what they deduced. And they called that substance phlogiston. And so they thought that heat was really this release of phlogiston from inside of the log or inside of whatever you were burning. Well, turns out it's not true. What happens whenever you burn anything, you always have anything that you burn like this is some sort of a carbohydrate. Okay? And when you add to it oxygen, this is not a balanced equation. Don't show Uko or Dr. Cuddy what I'm doing here. Just making a point. When you take some sort of a carbohydrate and you combust it with oxygen, what you get as a result is carbon dioxide and water plus the release of energy. All right, so what you're really losing between here and here is not phlogiston, but it's carbon dioxide and water and on oxygen, which of course are, I'm sorry, it's not oxygen over here. I was looking at that, I was like, what's wrong with that? There we go, that's better. Carbon dioxide and water, which at higher temperatures is a vapor, and so therefore it just floats away. So that's kind of cool. Now, if you do not have enough oxygen, if the reaction is oxygen starved, instead of getting carbon dioxide, you will get some carbon monoxide, still get the water, and if it's really, really bad, you'll get carbon, elemental carbon, which is called carbon black, and water, because the water bond is there's a lot more affinity for the oxygen to form with the hydrogen. Carbon bonds really well with a lot of different things, but also releases those bonds really well. So this is how carbon dioxide, or carbon monoxide, which is very dangerous, occurs out of combustion. So the big thing to have properly operated equipment is also to make sure that you're not reducing the amount of oxygen available to that reaction. And carbon dioxide, if you think about oxygen, O2, which our bodies like, carbon dioxide is a lot heavier than oxygen, so our body recognizes it in a different way. However, carbon monoxide is similar to oxygen. It's not very similar, but it's similar in weight, and our bodies tend to not separate it out in the same way. It tends to take it in the same way that you take in oxygen. So that your tissues and your body functions that require oxygen, the oxygen is actually replaced with carbon monoxide, and that's why people get carbon monoxide poisoning. That's why it's dangerous. It actually is a suffocation process. So, and that's why, like, if anyone's ever been gassed, they call it, carbon monoxide, you'll get really sleepy, and you start to get a headache because, and then you start to hallucinate, and then you're right, but that's it. I mean, you just want to go to sleep. So that is a dangerous part. So, yeah.
What's a combustion that would produce carbon black?
Yeah, if it's really starved. Like if you start to see, if you have a furnace, an old furnace, for example, and you put it in a closet, or if you have a water heater, a gas water heater, and you put it in a closet and close the door, you can starve the oxygen out so that when it kicks on, you can start to form carbon black. So anytime, if you ever find black elemental dust on anything, like if you move into an old apartment or something like that, and you find that, it's a very bad sign. And the easiest fix for it is just to open a door. Yeah. The other thing is it'll sometimes accumulate. not carbon black, but carbon monoxide. If you look over here on the chart, what you'll see is carbon is over here, it has a weight of 12, and oxygen is over here, it has a weight of almost 16. So carbon monoxide is slightly lighter than oxygen, because oxygen occurs as O2. So it'll kind of rise up. And so another situation where that will, where you can get bad problems with carbon monoxide situations is like if you live in an apartment, if you're on the 4th floor, and if there's a little bit of carbon monoxide being made all the way up, if you have like a pipe that has a leak in it, like an exhaust pipe that has a leak, it'll accumulate in the top part of the structure. So that's another thing. But yeah, carbon black, you have to really starve the heck out of it. I mean, what that combustion, what an incomplete combustion really wants to do is to form carbon monoxide. Elemental carbon or carbon black, you really have to starve it to death. So, or you have to have a malfunctioning appliance. But if you ever see dust like that, open up some doors really quick. So,
isn't carbon black how they make like tar cloth?
Yes,
stuff?
exactly.
They just
Yeah.
put it in the container.
Yes.
And then put it in the fire.
Exactly. Yeah, very, very good. So, yeah. So, I mean, it has its place. You just don't want to be, if you see it, what it really means in your house is that you're probably using carbon monoxide as well. So, very good question. See? But yeah, elemental carbon like that is kind of one of the main ways that they make it. It's like commercially. So, just sort of starting the reaction and come off just like that. You can burn anything. I mean, you know, that's the weird thing. I mean, you can, if you look at different societies, they've, you know, not everybody's always had big trees that they can cut down and put in a big old fire. You know, people burned peat and buffalo dung, and I mean, anything that's has a content of carbohydrate, you can burn if you can dry it out enough. So, anyway, good questions. All right, so sort of we will have homework tonight, but sort of to conclude our lecture for today, hang on just one second. I just want to make sure there isn't anything else here that I want to talk about before we get into homework. Nope, we're good. All right, so sort of to conclude our talk for today, for a closed system, meaning no mass is entering or exiting. The only way that you will have energy enter or leave is through heat and work. For work, an expansion is positive work. And you can see that from the integral that I drew for the work done by a piston. Pressure, we're talking about absolute pressure, so it's always going to be positive. So if dV, in other words, if dV is positive, meaning an increase in volume, that's positive work. If dV is negative, meaning a compression, then it would be negative. So there's the sign convention for work. Heat, if you add heat in to a system, it's positive. If you remove heat, it's negative. So think about the house. If it's cold outside, it's Q out to the house. If it's hot outside, it's Q into the house, right? So those are the sign conventions. They are fairly consistent. However, you have to make sure that you're using the proper form of the equation with the proper sign convention. So we'll be very consistent in this class. But it turns out, we know that all of the energy in a system at time 1 is conserved. So using this sign convention, if we say Q minus W plus E1 is equal to E2, all of our equations will work out correctly. And for simple mechanical systems, Q minus W equals E2 minus E1, which we've said in general is the change in, this is just delta E, I guess would be the way I would put it. So you could say delta potential energy, delta kinetic energy, delta internal energy. Internal energy is designated by the variable U. and I'll show you how to work with this. There are some equations that we can use to find internal energy. We also have tabulated data in the back of our textbook for some substances, which we'll get into a little bit later on. But this is the basic equation for conservation of energy for a closed system. Later on, we'll do open systems as well. And they're not difficult, but they just add some more elements because we also have to account for our mass going in and out and the energy associated with that mass. All right. So, I think that will get us to where we need to go today. And we're going to do a few homework problems, and just to kind of get us used to the ideas of heat, work, and different forms of energy. So the homework for Chapter 2 begins on page 97 and goes through page 109. And so what we're going to do today, we're going to do some conceptual units, conceptual problems, and then we are going to do some stuff working with units, and then a little bit of stuff starting to talk about putting together some problems for these ideas. So there are the conceptual problems at the beginning, 2.1 through 2-9, 2-1 through 2-9, which are just kind of short answer problems. 211 is a potential energy conversion problem. And we need to do some with some different units. So we're going to do 240E. In your textbook, and I want to do one more problem. Maybe two more. I want to do two more. 242E, and then 247. Okay? So these, when the problems have C's after them, that means concept. Those are going to be short answer questions. When there's no letter after it, it just means it's a regular SI unit problem. And E means English units. So just so you can kind of brace yourself for those. So the C's will go pretty quickly. They're not really math problems. They're just short answers. And then, so there's really like 9 short answers and 4 problems, 2 of which are in English units, 2 of which are in SI units. All right? All right. So any questions? All right, well, you guys have a wonderful day. Now, today is Thursday, and Friday and Monday, I'm not going to be on campus. I am completely available by email and by texting. So if you need to get a hold of me, do not hesitate for any reason to do so. All right? And otherwise, we'll see you guys Tuesday.